So ground fault protection, the evolution of ground fault protection technology. Here we go. So when installing electrical systems, we are always fighting against the following enemies: ground faults, arc faults, overcurrents, overloads, and overvoltages. And I've given the articles regarding each one of these, of course, Article 210.8, Article 210.12, Article 240, and Article 430.31 for overloads, and of course, a newer article, Article 242 for overvoltages. Technology and NFPA 70 continue to advance to provide the highest level of protection to personnel and equipment from these issues. In this presentation, we'll focus on ground fault protection and the various levels of that protection. So the origin of ground fault circuit interrupters. The ground fault circuit interrupter was invented by Professor Charles DeZiel and patented in 1965. He was an internationally recognized expert in electrical shock who worked with General Electric, the San Diego Electric Company, and the National Defense Research Committee, as well as a professor at University of California, Berkeley. He stated the GFCI interrupts power to prevent a lethal dose of electricity, specifically before the electricity can affect your heartbeat. He was a pioneer in understanding electric shock in humans and author of The Electric Shock on Man. The book was based on human subjects, including himself. He had come to realize that the most common cause of such deaths came from ordinary household circuits under the malfunction known as ground fault. His research objective then became to create a device which would interrupt a ground fault current before it was large enough to cause human physiological damage. It was a tall order. The problem-solving item needed to be sensitive, speedy, reliable, and cheap, based on a magnetic circuit plus a then newly developed semiconductor device. Remember, this is the 1960s. His GFCI did the job safely, reliably, and inexpensively. In his study, he conducted a series of tests to determine the minimum current required to produce ventricular fibrillation of the heart. Based on an earlier study he had done titled AC Shocks of Varying Perimeters Affecting the Heart Using Sheep and Other Animal Subjects, he determined that the sheep's heart is most vulnerable during what is known as the He phase of an electrocardiogram. Out of that research, he was led to invent the ground fault circuit interrupter, which he patented in 1961. And this graphic is showing basically how a GFCI works. If you'll notice, there is, of course, the hot conductor or current carrying conductor, and then the grounded or neutral conductor. And if you'll notice that circle, that sensor, that's called a current transformer, that device is wrapped around the hot and the neutral. That is how it determines when it should trip, is it is reading between the hot and the neutral. Just 3 years after DeZiel received his patent, manufacturers produced a commercially viable product that the National Electrical Code then required swimming pool underwater lighting systems to have ground fault protection installed. The first introduction of GFCI protection. Basic numbers discovered through his research was the resistance of hand-to-hand or hand-to-foot is about 1,000 ohms. It was also found that the heart works on 40 hertz, which is not too far from the 60 hertz cycle used in North America. So we are very close to tuning the AC circuit to the hertz cycle of the heart. It was found that around 30 milliamps of 120 240 volts at 60 hertz can cause fibrillation, and it can be as low as 1 milliamp if it is a direct enough path. GFCIs work on a 5 milliamp threshold. Typically around 10 to 20 milliamps, you reach what is termed as let-go threshold, when the current will create a muscle contraction that you will not be able to override. It's about 1 milliamp per 10 pounds. In 1965, there were 1,071 accidental deaths due to electric current, which was an increase from the previous year of 849. The NFPA began calling for DeZiel's new invention to be used in various areas, especially those involving water, as it is the main cause of ground faults. Starting with swimming pools in 1968, the NEC has been updated throughout the years to recommend GFCIs in a variety of locations. Now, jumping to UL, or the Underwriters Laboratory, and GFCIs. So the required use of GFCIs in residences dates back to the 1970s, but their use has been limited in commercial and industrial buildings because of the voltages involved. Class A GFCIs only operate on a maximum of 240 volts. We're going to unwrap that here. So GFCIs for residential use are listed as a Class A device under UL 943. That is one of their rulings, laws, and are limited to circuits at 240 volts. Anybody recognize this bathroom? Of course, Class A GFCIs do find use in commercial buildings. Their use has expanded nearly every code cycle for the last 10 years, but only on systems maxing out at 240 volts. But not all equipment is powered by 120 or 125 VAC. Submersible pumps and large decorative fountains use integral horsepower motors running up to 460 volts, while pumps in large commercial water slides may run 500 horsepower or more and at 460 volts or even greater. Wastewater plants often use pumps running at these voltages. Other higher voltage equipment that presents an elevated risk of electric shock includes wet saws, processing equipment handling wet material, and arc welding receptacles. Shock risks are also present in wet work areas with large portable fans or heaters and in any area where machinery is subject to washdown cleaning. I've seen that in some manufacturing plants I've been in where they actually manufactured, what they actually did was they were food manufacturers. And therefore, there's a lot of washdown happening there, because of the cleanliness, rules that they have regarding their product. All these areas would benefit from GFCI protection, yet a Class A GFCIs are unsuitable for these applications for several reasons. UL 943 versus UL 943C. These are two separate rulings from the underwriter's laboratory. So UL 943 standard applies to Class A single and three-phase ground fault circuit interrupters intended for protection of personnel for use only in grounded neutral systems in accordance with the NEC. And these devices are intended for use on AC circuits of 120 volts, 12208, 12240, 60 hertz circuits. UL 943C requirements cover ground fault circuit interrupters intended for use in one of the following applications. Number one, on grounded neutral systems where voltage to ground is above 150 volts and equipment grounding or double installation is required by the NEC. Or number two, on grounded neutral systems where voltage to ground is 150 VAC or less and equipment grounding or double installation is provided, but the use of a Class A GFCI is not practical. UL 943C, Special Purpose Ground Fault Circuit Interrupters, was introduced to address the two limitations of Class A GFCIs that prohibited their use in many industrial applications, namely the system voltage limitation to a maximum of 240 volts and a maximum allowed leakage current of 6 milliamps. UL 943C defines three GFCI classes, classes C, D, and E. These new classes are rated up to 600 volts with a trip level of 20 milliamps. In addition, UL 943C requires the device to monitor the continuity of the ground wire and interrupt power to the load if ground integrity is lost. At voltages greater than 150 volts, the resistance of the human body decreases dramatically and the fault current flowing through the body increases to unsafe levels requiring impossibly fast trip time. The resulting current through the grounding conductor will also trip the GFCI to eliminate the danger of fibrillation. Ground fault circuit interrupters, this is from Article 100, Special Purpose Ground Fault Circuit Interrupters, a device intended for the detection of ground fault currents used in circuits with voltage to ground greater than 150 volts that functions to de-energize a circuit or portion of a circuit within an established period of time when a ground fault current exceeds the values established for Class C, D, or E devices. And here is said device. This is a product from Littelfuse, and this is the term they use for it is a shock block, but this is essentially the unit that is known as a special purpose GFCI device. I've looked around online a little bit. I haven't purchased one of these yet, but basically I haven't seen one for less than $2,000. I can say that. You can see where they have the input, A, B, and C phase coming in. and then the output here on the secondary side, and then here are the terminals where your ground conductor would be installed, and it passes through the unit also. The SP6100 detects leakage current and interrupts the circuit, significantly reducing or eliminating the shock potential. One key part of the additional safety features of this unit also monitors the ground wire from the SP6100 to the load for continuity. If the wire is broken or becomes loose, there will be a signal and an alarm and interrupt power. So, a Class A GFCI that will interrupt the circuit to the load when the ground fault current is 6 milliamps. This is the standard GFCI we've been using. So a GFCI that will interrupt the circuit to the load when the ground fault current is 6 milliamps or more, but not when the ground fault current is 4 milliamps or less, and is intended to be used in circuits where the line-to-line voltage is 240 volts or less. Class B is a GFCI that will interrupt the circuit to the load when the ground fault current exceeds 20 milliamps, only used with swimming pool underwater lights that were installed prior to local adoption of the 1965 edition of the NEC. This version, the Class B, is obsolete. And this is Class C, D, and E. A Class C for use in circuits with no conductor more than 300 volts to ground, where reliable equipment ground or double insulation is provided. A Class D is for use in circuits with one or more conductors more than 300 volts to ground and with specially sized reliable grounding to provide a low impedance pass so that the voltage across the body during a fault does not exceed 150 volts. And a Class E for systems similar to Class D, but with special high-speed tripping required that eliminates the need for the oversized ground of Class D. Class C, D, and E GFCIs trip at 20 milliamps rather than 6 milliamps trip current mandated for Class A GFCIs. This increase in GFCI trip level is allowed by UL assuming the availability of a reliable ground in parallel with the body. During a fault, the grounding conductor will shunt the fault current around the body and cause the device to trip. This provides the let-go protection, while the 20 milliamp threshold provides against fibrillation. If there is no grounding conductor, such as in two-wire household products, then the GFCI must provide both let-go and fibrillation protection, and a Class A device would, of course, be required. The danger caused by electric current passing through the human body depends on both current and time. Currents of 0.5 milliamps or less are harmless and generally imperceptible. Currents from 0.5 up to 10 milliamps or more, depending on duration, may cause involuntary muscle contractions and possible injury from striking near objects. Currents just beyond this will likely cause ventricular fibrillation. The trip curve published by UL for GFCIs was designed to keep current through the body to safe levels, prescribing GFCI trip times that decrease with increasing current. So SPGFCI protection. This next level of protection from ground faults is now a part of our code. And this is one of those devices right here. You can notice it still has the test and reset button on the front of it. Okay, this next segment is really just bringing it forward into some new technology that is fairly recent regarding the testing of GFCIs. So when UL 943 was adopted, it was assumed that GFCIs, like other consumer products, have a limited life expectancy and at some point no longer provide protection. Therefore, UL imposed a provision that manufacturers include a way for end users to check for proper operation of the devices. And of course, the Test Monthly title was born. I thought it amazing that DeZiel determined that the devices would not last forever. Unfortunately, even if the end users did test monthly, a device that did not test properly could still be reset without providing protection. Studies going back as far as 1999 showed significant numbers of devices provided power without GFCI protection. If they received a lightning strike to the home or a line surge or some type of power surge in the system, GFIs could be damaged but still appear to be working but not be providing GFI protection. Some of the older ones also, if you wired the line and load backwards, they might still work. And that was the problem, that if you could plug in your testing device downstream and hit the test button and it trips out, that may make you think that the device is working properly. And some may not go to the actual GFI device itself and test because they think, well, I tested it downstream, it's working fine. When in reality, if you wired the line and load backwards and you tested the face of the GFCI itself, it would not trip. devices now are required to actually not work if they are not wired properly. In 2015, the new Underwriters Laboratory standards require newly manufactured GFIs to be auto-monitoring self-testing by conducting an internal test to confirm that protected power is available. UL 943 also contains requirements for power denial to the GFCI receptacles and any downstream connected devices when the GFCI reaches end of life. GFI devices are known to wear out, stop working over time. One of the reasons we're supposed to be testing them. I saw a video some years ago of I believe it's an engineer with Schneider Electric, and he had said he just bought a new home and had lived there for a couple of years, and he had already replaced all of the GFIs in his house. He said because he was, he's an engineer guy, one of those type of people, very, diligent, and was testing everything regularly. And over time, he had determined that they had needed to be replaced because they were not working. I thought that was very interesting. And, you can only imagine how many people out there are not doing that. So we now have this product out today, and I just picked Leviton as a random brand. There's lots of other brands out there that are doing the same thing, but this is their description from their website about their self-test GFI. And it says a self-test GFCI receptacle has all the features of a conventional receptacle, but in addition, this receptacle performs a self-test every 15 minutes to confirm the GFCI electronics are functional. And there are two indicator lights on the face of the GFCI device. The first light will flash green or red to indicate the status, and the second light will flash amber to indicate a trip or fault. When the device is first wired up or in a tripped condition, the green status indicator light and the amber indicator light should be on. Pressing the reset button fully should turn the amber trip indicator light off, and the status indicator light should remain green. How many people do you think really understand all of those little lights on the face of your GFCI devices, let alone the ones that are on your GFCI breakers or your dual function AFCI GFCI breakers? The self-test GFCI receptacles should still be tested every month. Press the test button and the amber light should come on, and pressing the reset button should turn the amber light off, and the green indicator light will stay lit throughout this test. This will ensure a functional GFCI receptacle. Interesting. GFCI receptacles and breakers manufactured prior to the June 29, 2015 effective date bearing the UL certification listing mark were not required to meet these new requirements and may still be in the stream of commerce until supplies are exhausted. Well, you better believe if there was still some on the shelf at the Home Depot or Lowe's, they're not going to throw those in the garbage. They're going to sell them until they're gone. GFCI protection has provided life-saving technology to our electrical systems for decades. It is a natural progression to expand into higher voltage levels and commercial industrial installations. The takeaway from this would be the Class A GFIs are operating at a 4 to 6 milliamp level. In other words, it exceeds that 5 to 6 milliamps amount, and that's when it's going to trip out. The SPGFCI, or Special Purpose GFCI device, is going to operate at 20 milliamps. And one thing you might notice when you get in front of one of these SPGFCI devices is that they have a dial on them to where you can set that. Now, there is another one that we really hadn't discussed, and that is GFPE, or Ground Fault Protection for Equipment. Obviously, by the title, that's not providing protection for human beings. That's providing protection for equipment. That can be at as much as 30 all the way up to 100 milliamps. And products like that are used, for example, Article 555 in marinas and boatyards, used on docks and boat slips where you have protection that needed to be provided for equipment. And then when it gets to the actual boat slip itself, that's when you actually will see the Class A GFI protection. So I hope this video has been helpful in bringing some knowledge, or maybe some new knowledge to you regarding GFCI protection. And be sure and like and subscribe, and check out our website at electriclab.org. I'm Mike Barley, and thanks for watching.